All right, in this discussion, we're going to talk about balancing chemical equations. I'm going to show you a couple ways to do this. And then we're also going to talk about reaction rates and factors that affect the rate of a chemical reaction. So diving right in, when we balance equations, really our goal is to observe the law of conservation of mass. We're making sure that we have the same number of each type of atom on both sides of the equation, right? Because we can't have atoms of a specific type appearing out of nowhere or disappearing into thin air, right? And the way that we do this is we add coefficients in front of molecules to change the number of molecules. When we balance an equation, this is the only thing we can change. So coefficients and subscripts work really differently. So subscripts cannot be changed once the equation is written. If we were to change the subscripts, we would change the identity of the substances. So let me sort of explain what I mean by this. For example, if I were to have water, I'm just going to write this at the bottom of my whiteboard. Okay. If I wanted to balance, I'll give a different example. If I wanted to balance this equation, H2 plus O2 yields H2O, you might think, well, that's fine, that's easy, I can just put a 2 here. But you can't do that. And the reason that that doesn't work is that doing that actually changes the identity of the substance that we have, right? H2O2 is hydrogen peroxide, and we are talking about water. So instead what we do is we add coefficients. We would put a 2 here to get 2 water molecules to balance the oxygen, and then we would put a 2 here to balance the number of hydrogens. So the coefficient applies to the entire molecule. Now, a couple of helpful tips. When we balance chemical equations, we want to start with atoms that are only found once. So typically we would do hydrogen and oxygen last. Those tend to be the ones that appear multiple times most frequently. In combustion reactions, which we'll see lots of examples of those, you're going to balance in the order carbon, hydrogen, and then oxygen. We'll talk more about the details of that soon. If we have a polyatomic ion on both sides of the equation, treat it as one unit instead of breaking it into separate atoms. So for example, you would say, I have 1 sulfate, not 1 sulfur and 4 oxygen. Double check your work at the end to make sure that we have the same number of each element on each side of the equation, and reduce the coefficients at the end if necessary. So for example, if your coefficients are 2, 4, and 2, you would reduce those coefficients to 1, 2, and 1. All right, so looking at these, pause for a moment and see if you can figure out which equation is balanced. Now the first equation is not balanced because while the 2 in front of sodium chloride balances the chlorine, I now have 2 sodium atoms on the right side of the equation, the product side, and only 1 on the reactant side. In the second example, oxygen is not balanced, and so the equation that's balanced is the third equation. Sometimes the way this question might be asked on a test is we might ask you which equation correctly shows the law of conservation of mass. All right, so I'm going to do a couple examples on the whiteboard of balancing chemical equations. So these are in your guided notes packet, so you can take a look at these, and then I'll have a little practice for you to do as well. All right, so the first example is aluminum plus oxygen yields Al2O3. Sorry, there's a little bit of a glare there, but we'll just have to live with it, I think. Now, some people like to balance using the inventory method. So what that means is that I'm going to sort of just keep an inventory or some kind of a tally of how many atoms of each type I have on both sides. And I like to draw that line down the middle to sort of show where the dividing line is, right below the arrow. All right, so at the moment, I have 1 aluminum atom on the left, and I have 2 oxygen atoms since it's O2. On the right side, I have 2 aluminums and 3 oxygens. Okay, so I can see right now that neither atom is balanced. So I can start wherever I want. It's going to be easier to start with oxygen, so that's just where I'm going to start in this example. Now, I have 2 here and 3 here. No matter what I put in front of O2, I'm going to get an even number of oxygens. Okay, so we have to get 2 and 3 to balance out. You can think of this like finding the least common multiple, right? We have to get these oxygens to the same number. The easiest way to do that is going to be to get them to 6. So if I put a 2 here and a 3 here, that'll give me 6 oxygens over here, and 2 times 3, 6 oxygens here. Now, since that applies to the entire molecule, what that means is that I'm now going to have 4 aluminums, because when I write 2Al2O3 like this, it's like saying I have Al2O3 and another Al2O3. Okay, so what that means is that I would then wind up with 4 aluminums and 6 oxygens. All right, so now oxygen is balanced, so the only thing that I would have to do at this point is balance aluminum, and I can do that by putting a 4 here. So now the equation is balanced. Now, you don't have to do this inventory. I find that a lot of people like this, particularly as they're sort of like getting more comfortable with balancing equations, but if you feel comfortable without it, it's certainly not required. All right, so the next example, I believe, is the sodium one. So my next example here is sodium plus water yields sodium hydroxide and hydrogen. All right, so this one's a little complicated just looking at it, because on the right side I have hydrogen in 2 places. So I'm going to need to kind of be careful of that as I balance. All right, so I have sodium, hydrogen, and oxygen. And when you do your inventory on the right side, I would suggest keeping those atoms in the same order, because if you mix them up, you might get a little confused. It's easy to do. All right, so initially I have 1 sodium, 2 hydrogens, and 1 oxygen. On the right, I have 1 sodium. I have a total of 3 hydrogens, 1 from sodium hydroxide and 2 from H2, and I have 1 oxygen. All right, so the only thing right now that's not balanced is hydrogen. So we kind of have to start there, which is a little bit unfortunate, but such is life. All right, so when I look at water, I see that no matter what, again, I have to have an even number of hydrogens. And over here I have an odd number. Now, since hydrogen is split up, I can only change one of these hydrogens. So what I'm going to do is I'm going to put a 2 here. And the reason that I'm going to do that is that that will give me an even number of hydrogens, because I'll have 2 here and 2 here. So that gets me to 4 hydrogens. Now, because I put the 2 in front of sodium hydroxide, I now have 2 sodiums and 2 oxygens. All right, so let's balance hydrogen by putting a 2 here. When I do that, I have 4 hydrogens and I now have 2 oxygens. So hydrogen and oxygen are balanced, so the only thing that I need to fix now is sodium, and I can do that by putting a 2 here. When 2 things are separated by a plus sign, when they're separate molecules, the 2 only applies to that substance. So the 2 here doesn't apply to water, okay? They're separate substances. All right, so what I would like you to do is to try balancing this equation. Just pause, do this in your notes, and when you're ready to see the answer, press play. All right, so this is the final answer, and here's why this is correct. First, I put a 2 on the right side in order to balance the copper and, in order to balance the oxygen. And then I put a 2 in front of the copper on the left in order to balance the copper. All right, now these are combustion reactions, and these are a very specific type of reaction where a hydrocarbon reacts with oxygen to produce carbon dioxide and water. So when you see one of these, you're going to want to balance these in a specific order. Always balance in the order carbon, hydrogen, and then oxygen. Okay, so let me show you on the whiteboard how you would set this up. All right, so when I look at my inventory, again, I'm going to write it at CHO because that's the order that I know I want to balance in. I have 7 carbons, I have 16 hydrogens, and I have 2 oxygens. So as you can see, these numbers, they're going to get pretty big. They might be bigger coefficients than you're used to seeing. And then on the right side, I have 1 carbon, 2 hydrogens, and this is where you have to be super careful. I have oxygen in 2 places. So right now I have a total of 3. Now I'm not going to worry about that because I know I always want to balance this in the order carbon, hydrogen, and oxygen. All right, so I'm first going to put a 7 here to balance carbon. And I'm just going to count up the oxygen at the end once I've balanced hydrogen, save myself a little bit of time. All right, so I have 16 hydrogens here and only 2 here. So I'm going to put an 8 here to give me 16 hydrogens. Now, this is where you have to be careful and where people most frequently make mistakes. So when I'm counting my oxygens, I have 7 times 2, so I have 14 there, and then I have 8 here. So I have a total of 22 oxygen atoms. So in order to balance this equation, I need to put an 11 here because that will give me a total of 22 oxygen atoms. Okay? Now, again, these coefficients are higher than ones we've seen. Don't be, alarmed or put off by that. That's totally normal. All right, so let's look at this next one. Now, this is going to look a little bit different. We're still going to balance in the same order, and I'm not even going to do the inventory at the bottom. I'm just going to count the oxygens when I get there. All right, so I have 6 carbons here, so I need to put a 6 in front of CO2. I have 6 hydrogens here, so I need to put a 3 in front of water, because 3 times 2 is 6. So when I count up my oxygens over here, I have 12 plus 3, so 15. Now that kind of creates a problem because there's no whole number coefficient I can put in front of O2 to give me 15 oxygen atoms. When this specific situation happens with combustion where you have an odd number of oxygen atoms, you're going to put a 2 here and then double your existing coefficients. What that's going to do is that's also going to double the number of oxygen atoms. So now I have 30. So my coefficient in front of O2 will be 15. And when you look at this, you can't reduce those coefficients any further. Now, again, if you're not expecting it, that coefficient seems really high, but don't be alarmed by that. You're doing it correctly. All right, so those are the ones that tend to take the most practice for people. So that may be something that when I'm back in class, you may need to get a little extra help on. All right, so I want you to pause for a minute and try to balance this combustion equation, again, using the same order, carbon, hydrogen, and oxygen. And when you're ready to see the answer, you can just press play. All right, so when I balance this, I put a 2 in front of CO2 to balance the carbon, and a 2 in front of water to balance the hydrogen. So then I wound up with a total of 6 oxygen atoms on the right side, so I put a 3 in front of O2. Now the last big sort of trick is when you're balancing equations with a polyatomic ion, it helps to treat the polyatomic ion as one unit. So I'm actually going to demonstrate this on a piece of paper because I ran out of whiteboards. So let's take a look. All right, so this is my equation. And when I balance this and I do my inventory, I'm going to look at, I have sodium, I have phosphate, I have calcium, and I have carbonate. So I'm going to treat this phosphate unit, PO4, as one thing. Then on the right, I'm going to keep them in the same order. I have sodium, I have phosphate, I have calcium, and I have carbonate. So initially I have 3 sodiums, 1 phosphate, 1 calcium, and 1 carbonate. On the right, I initially have 2 sodiums, 1 phosphate, 3 calciums, and 1 carbonate. All right, so I'm going to start by balancing sodium. Now again, I'm going to have to do that least common multiple thing because I have 3 here and 2 here. So I'm going to put a 2 here and a 3 here to give me 6 sodiums on each side. Now that also changes the number of phosphates, so I now have 2. And over here I have 3 carbonates. Okay, so I can just balance phosphate next, why not? So I'm going to put a 2 here to give me 2 phosphates. That's also going to mean that I now have 6 calciums. All right, is that right? Yeah. All right, I am just kidding. I forgot to put the phosphate subscript here. There's C3PO42. So that means that I actually didn't need to do that at all because phosphate was already balanced. So I just have 3 calciums. Okay. So now I have 3 calciums and 3 carbonates. So I put a 3 there and it's balanced. Sorry, that was probably a smidge confusing. I do apologize. It helps to copy down the formulas correctly. Okay. But again, the main point there is to treat it as one unit. All right, so I want you to pause for a moment and try to balance this equation. And again, here you have 2 polyatomic ions. You have nitrate and you have hydroxide. And just press play when you're ready to see the answer. All right, so by putting a 2 in front of sodium hydroxide, I balance the hydroxides. And then by putting a 2 in front of sodium nitrate, I balance both the nitrate and the sodium. Okay. There's lots of resources on Schoology to help you with this. And if you're having trouble with balancing, the video that you watched before the discovery might be super helpful to you. All right, so the last piece of this is talking about reaction rates. So a rate of reaction is the change in the amount of a product or reactant over time. Now, It's a measure of speed of a reaction, but it's really important to note that rate is expressed as change of amount over time. So sometimes people get confused with that and they want to express the rate just by saying the number of seconds or minutes the reaction took. But if you asked me what my speed was driving to work in the morning and I said it was 10 minutes, you would say that's not a speed at all. You'd be expecting me to answer in terms of miles per hour, some kind of distance or amount over time. So whenever you're trying to calculate a reaction rate, you can look at the amount of the reactant that is reacted in a certain amount of time or the amount of product that's formed. So it's just a pretty simple amount over time division. Now the units could really vary depending on what the units of amount and time are, right? If it's really fast reaction, your time units are probably seconds. If it's slow, it could be minutes or hours. And then in terms of the amount, maybe we're looking at mass, maybe we're looking at volume. It really just depends on the reaction. Now there's 4 major factors that influence reaction rate: temperature, surface area, concentration, and the presence of a catalyst. Now, in order to understand reaction rates, we have to understand collision theory. So collision theory has 3 major principles. First of all, in order to react, the reactants have to collide. If the reactants are really far away from each other, they can't possibly have a reaction. Additionally, they have to collide in the correct orientation, and they have to collide with enough energy to overcome activation energy. You might remember learning about activation energy in biology when you talked about enzymes. Now, the first factor that influences reaction rate is concentration. So the concentration is just a measure of the number of particles in a given volume. So something that's highly concentrated has a lot of particles. Something that has a low concentration might have very few. As concentration increases, the rate increases. And I think this is kind of intuitive for a lot of people because if there's more particles in a given volume, there's going to be more collisions, right? Imagine that we were walking around our classroom with blindfolds on. We would collide with each other, right? If we invited the class next door to also come into our room, put on blindfolds and walk around, we would collide even more because there'd be more people in the same volume to collide with. Now, when we change the surface area, that also affects the reaction rate. Now, you probably know about this just from cooking, right? If you've ever tried to cook, like if you're not a vegetarian, or even if you are, if you've ever tried to cook meat or tofu, and you have a really large piece of that, in order to make it cook faster, you would do what? You would cut it up, right? So when you do that in cooking, you're really just increasing the surface area. So we increase surface area by crushing something, chopping it, grinding it. Any of those verbs mean that we're increasing the surface area. Now, as we increase the surface area, the rate of reaction is also going to increase. And the reason is when we increase the surface area, we're making more particles available for reaction. There are more places that a reaction can occur. All right, so which of the following would lead to the fastest reaction rate? So pause for a minute, and then when you think you know, press play and we can go over it. So the correct answer is A. Both surface area and concentration increase rate. So if those are both high, then we would have the fastest rate. The third factor is temperature. And as temperature increases, we know that molecules move faster because temperature is just a measure of the average kinetic energy. So as temperature increases, the rate of reaction increases really for 2 reasons. Reason 1 is that more collisions will occur, right? So imagine again that we've put on blindfolds and we're walking around the room colliding with each other, okay? If we start running, moving faster, we're gonna collide even more, right? Because we're moving more quickly. It's just more likely that we'll collide. But the second thing that's true is that those collisions are going to have more energy. The molecules are moving at higher speeds, they have more energy. And therefore, those collisions are more likely to be successful in overcoming activation energy. They're more likely to have enough energy that they can actually react. Now, when we talk about activation energy, we also want to talk about our fourth factor, which is adding a catalyst. So a catalyst is something that speeds up a reaction, but is not changed or consumed by that reaction. So in biology, you talked about enzymes. Enzymes are biological catalysts. So how does a catalyst work? A catalyst provides an alternate reaction pathway that requires less activation energy. So this diagram, I think, shows it pretty well. The blue line represents the activation energy that would be required for this particular reaction without a catalyst, and the red line shows the activation energy that would be required with a catalyst. So because less energy is required, more collisions will be successful and the reaction will speed up. It doesn't actually give the particles more energy, it just means that some particles that wouldn't have reacted before will react now. All right, so the student wants to carry out a chemical reaction in the lab. Which of these would not increase the reaction rate? So B is the correct answer here, because if we use larger pieces of a solid, we actually have a lower surface area. A, C, and D are all examples of favorable conditions for increasing reaction rate. All right, so I want you to do your best, try the practice paper, see what questions you have, and of course, you can always send me an email even if I'm not there to answer your questions.